Hey guys, Professor Doney back again. We're in the middle of talking about Newton's laws of motion. There's three laws. Sum of the force is equal to zero, law of inertia. Sum of the force is equal to ma, that's Newton's second law, and the third law is equal and opposite action or reaction. Alright, so what we have is our 10 kilogram box still, and what I have is resting on the floor of the table. We still don't know anything about friction, so don't worry about that. How do we know? Because we haven't mentioned it. There isn't anything said about it. We have three forces acting on this besides the force of gravity and the force of the table holding the box up. And 10 to the right, 5 to the left, a 10 up. Okay? And what we want to do is look at this box and analyze it and see if it's going to move or not. So we want to always start out by drawing ourselves a free body diagram. Since it has mass, it'll have the force of gravity, or mg, down. Since it is resting on the table, we'll have the normal force, or the force of the table holding it up. I'm going to start to draw it this way, and we call that F of n. And to the right we have a 10, and to a 5 we also have a 10 up. But what I'm going to do is, while I'm making this drawing, is, well, actually we do that later, never mind. There's a 10, and here's the 5. Okay, so basically what we did is create a free body diagram by freeing the object up, freeing the body up from what's touching it, and replaced it with a normal force and put gravity in there. Alright, again we're going to start off in the y direction and look at summing the forces in the y, and we're going to set it equal 0 and call positive up. Now, why do we start in the y direction? Well, when we start looking at friction later, we need to find the F of n before we can get friction, and we need to know friction before we can move the box. But basically it makes our life easier down the road, so we're going to just stay with solving in the y direction first. Alright, pick positive up. We're going to assume that it's not going to lift off. So assume no lift off. Okay? A-N-L-F. Assume it's not going to lift off, it's not going to leave the table. So let's say it's not going to move. That's why we set Newton's first law. Alright, up we have a 10. We also have the F of n up, and we have minus mg down, and it's saying if it doesn't move it has to all equal 0. Anything vertical, 1, 2, 3, has to show up in this equation. I'm going to solve for F of n. That equals mg minus 10, since it's a 10 kilogram box, times gravity 9.8 minus 10. I should get, I think, 88 newtons. Now what does that mean? The F of n is the table holding it up, or the scale holding it up. It basically tells us what does this box weigh, or appear to weigh, or how much does the floor have to hold up. When I step on a scale, I weigh, let's say, 200 pounds. If my kid gets on my back, I'll weigh 250. Is that my true weight? No. It's what I appear to weigh based on what the scale has to hold up. Now, as long as that number is greater than 0, we don't have to worry about it lifting off the table and causing some other issues. So we're good there in the y direction. Let's look in the x direction. Pick a little different color. Alright, what's happening in the x? Well, we're going to pick positive to the right, and we're going to look at this now. Since everything is horizontal and all cleaned up, I have a 10 to the right, 5 to the left. If I sum those and set them equal to 0, obviously I find out that I have a minus 5 plus 10 equals 0, which is not true. Alright, that comes out to be a 5 does not equal 0. Since that's not true, we have to say, hey, it moved, and if it moved, we have to sum forces in the x equal to Newton's second law. If things move, we move on to Newton's second law, F equals ma. And we could have by inspection said, hey, if we pull to the right with 10 and only to the left with 5, there's a net of 5 pulling that way. So it will move. So we're going to redo this. We have 5 to the right. The mass is 10 times A. It tells us that A equals basically half a meter per second squared. That's the acceleration to the right. Tells us, hey, this thing will accelerate, and there's the acceleration rate. Okay? So we did have an unbalanced force. We do have a net force there. So it's a little different problem. We're going to get a little more confusing with putting some angles in here in the next installment. We'll see you there.